I guess a bunch of you know me already. I'm a principal engineer in Intel in the Software and Services Group. I work from my house here in Bristol. I've been in Bristol since 1979 when I came here to work for Inmos on the transputer. So a bunch of people who have been around Bristol will certainly know me. As we were saying, this presentation was originally prepared by Shuo and Brian, and Brian didn't get travel to come from the States, so I got drafted in, and after a number of interviews they decided that I could actually give a marketing presentation without adult supervision. So you can tell that I'm not actually a marketing person. Just look how I'm dressed, and I've got Dennis the Menace on, and you'll realise that that's not necessarily clear. So legal disclaimers, we have to show all of this stuff. I'm sure you've read it all. I'm going to run through fairly quickly, about 20 minutes, just giving you a general overview, and then Shuo is going to go through a detailed stepwise optimization scheme and how we think it's a good way to exploit the Phi and the Xeon Phi. You see, I've done it already. I shouldn't say Phi. I should always say Intel Xeon Phi coprocessor with R's and copyrights and things on there as well. So I'm going to try and get through in 20 minutes. If you have really urgent questions, then throw them in. Otherwise, we'll take lots of questions at the end. We'll also be around for the rest of the day, and we have a demo station out in the place where we were having coffee with a real live Xeon Phi running. Yeah. Okay. So this is just pointing out that as time goes on, we add more cores and more threads and wider vectors to the existing processors. So over time, we've gone from one core. These are server parts. So 1, 2, 4, 6, 8. It's happened more slowly, perhaps, than we were forecasting back in about 2000, when we were expecting that we'd have 16 or 32 cores in laptops by this point. But it's possible to put. It would be possible to put that in, but it turns out that you make more money by integrating the graphics. And one thing not to forget about Intel is that it's a company and it exists to make money. So we have a load of people who spend time working out, given this amount of silicon area, which part of the system is the best thing to pull in to make the die sell for the highest price, which is exactly the same thing that we were hearing about earlier. How do I maximize the return on my silicon? Critical point to note, though, for instance, is that we have even on the Xeon there, the current one, we have eight cores on the die, and we're doing 256-bit wide SIMD. So that's eight single precision, I think, is it? Is that right? 32, yeah, 8 single precision. So that's a factor of 32 down if you only use one core and don't vectorize. You're a factor of 32 off the peak that you could achieve on that part. Now, and that's the generic server part that's used by everyone, certainly used by most HPC people. Moving over here, and that's just a multi-core part. Moving over to the Manycore part, we have up to 61 cores on there. Each of them has 4 hardware threads, which are slightly different in intent than the threads over here. We can talk about that a little if you want. And we have a 512-bit SIMD width. So to get good performance out of this thing, you really need to have your vectorization. But that's not wasted effort because you needed it over here anyway. A wonderfully marketing graphic over here on the right, which I should ignore if I were you. Well, it tells you that we're going to do all these safer food supply. Okay, maybe. Interactive holographic images. I don't think so. 61 cores at 1.1 gigahertz. So note that that's slower than the other CPUs. You can't put that many cores on and have it go fast. 8 gigabytes of memory. And this is GDDR5 memory, and 352 gigabytes per second of bandwidth. So this is the same kinds of technology that are used in GPUs to get high bandwidth. We have ECC implemented as well. on the memory system. 5 12-bit SIMD instructions. But it's not. It's a coprocessor. It's not an accelerator. So it's an x86 processor. Most of my trusty 486 manual that I still have on my desk is exactly the same on this processor, and except that it's 64-bit. It's running Linux, so I can SSH into it. I can use it as a node in an MPI program. So all of that effort that we were having described in the previous presentation about how hard it is to move stuff through MPI from the GPU to somewhere, well, just run an MPI process on the thing. It can be your MPI. It can be MPI processes in your MPI system, and just compile for it. Standard programming languages and tools. So we'll talk a lot more about that. And it has all these great performance things. I should point out that we're very scrupulous about these ratios and what we talk about, and that's a lot of what these things that no one can read on the bottom is detailing exactly what we're talking about when we do these comparisons. So you should be able to find out and replicate these results yourself. We will tell you the matrix sizes that we're using for SGEMs and DGEMs and so on. So Intel really, really tries to make sure that you can replicate all of our results. Yeah, use this one or use this one. We'll move on. This is so way back to the same kind of time that was being talked about in the keynote with the connection machines. Intel built the first system that did a teraflop sustained, and it was a lot of Pentium Pro processors, 7,000 Pentium Pro processors. And now we've got to a teraflop sustained in one chip on the 22 nanometer process, which is the current mainline process. It's running Linux. It fits in a PCIe slot, and we did that last year. This year, we actually announced this as a product. It's available. General availability is January the 28th, so you can order them now. Talk to your OEMs. There are pricing on Intel's website for this part. 7 of the top 500 in the list announced in this November included Xeon Phi processors, coprocessors, and the number 7 on the list, which achieved 2.6 petaflops with an efficiency of 75%, is TAC. Is the TAC Stampede machine, which has a lot of Xeon Phis in it. It isn't fully built out yet, so we expect that to improve next year. And also, just to lay some lie to the statement that everyone makes that, oh, Intel processors can't be power efficient, the number 1 result on the Green 500 list, which rates machines by their energy efficiency, was the Beacon at NICS, and that uses Xeon Phi. And it achieved nearly 2.5 gigaflops per watt at a 70% efficiency. Here are some numbers from measured on TAC for LinPack and SGEMs and DGEMs. These are all with these are with ECC on, so stream triads with ECC on, and they're measured using the Intel Math Kernel library, so they're not a hand-rolled piece of specific code. They're using our Math Kernel library. Isn't that all great? Why don't I use it for everything? Well, this explains to you why you don't use it for everything. And the reason is that if you look over here, if you don't have any vector performance and you don't have any parallelism, you get something like 1/5 or 1/10 of the performance of the Xeon from a single core. Well, that's not that surprising. You know, the Xeon, we put 8 of them on there because that takes up most of the die, and here we're fitting 61 on there. Well, they must be a lot smaller to fit in the same area, and they are. They're much simpler processors. They're actually basically a Pentium 2, not even a Pentium 4, taken out of our design library, expanded to 64 bits, given 4 hardware threads, so many more registers, and given the big wide SIMD units. So it's an in-order processor, and those of you who remember those Pentiums, they had all these funny two-pipe and pairing rules. Those are all still there if you really want to go back and dig out your optimization guide from about 1992, maybe even earlier than that. You'll find that that still applies. So the processors are slow. And what that means is you need a lot of vectorization, a lot of parallelism before you improve performance. This is assuming that you're not memory bandwidth limited, of course. If you're memory bandwidth limited then, and have a reasonable amount of parallelism, then the extra memory bandwidth can help you. But otherwise, you don't get performance. You're better off staying on the fast, out-of-order cores that are very clever and can handle general codes. On the other hand, if you can get a lot of parallelism and a lot of vectorization, then you move down here and you start getting performance that's coming up to 3 or 4x the performance you would get on the Xeon. And if you can if your problem is using some of the specific architectural features that are in the Xeon Phi, so in particular we have some support for transcendental functions as instructions in there, then you can get performance that's up to maybe 6 or 7x over the Xeon. But it's work. Nothing's for free, right? It's easy to get code to run on the machine and get no performance, which is different from some other machines where you get 0 performance guaranteed until you've done a lot of work porting. Here, the port is generally pretty easy. Hello? Sorry,
can I just make sure I understand? This is comparing one core against one core?
No, this is comparing a Xeon die against the 2-socket server. Right? And this is a theoretical calculation. This is not measured. This is just, Amdahl, basically. It's just that managers don't understand Amdahl's law until you show it them as a graph. Right? So I could, for this audience, maybe I should have just said Amdahl applies. But even for this audience, it helps to see, whoa, I really need a lot of parallelism. I need 90% plus parallelism, and I need, 90% vectorization to get up to 5x or whatever that is. Yep. But real applications are running on these machines and seeing speed-ups that are non-trivial. So, these are the kind of levels of speed-ups up to 2 and a bit. And then the Black-Scholes 7x and the Monte Carlo, and these are because they're using and one of these is the one that Troy is going to show us in a minute. So before you need the right workload. It has to be parallel. It has to be vectorized, and you can do a lot of analysis on the current Xeon platform. So you can look. You can see you can use VTune. You can use the sampling profiler. You can look at the percentage of instructions that you're executing at a floating point. You can look at the available parallelism, and that's all great. And then you can move over, and we can use all of these standard things. OpenMP, I didn't mention, but I'm actually the architect for the OpenMP runtime at Intel, and that's, it's been a bane of my life that it's so easy to port things to this machine, because what happens is people take their code, their OpenMP code that scales well at 4 cores on the, scales at 50% efficiency at 4 cores on the server, and they recompile it, just add -m mic to the compilation switch, recompile, run it on the Phi, and they get absolutely awful performance. So what do? Next is they reach for the profiling tool, they profile it, and they go, all the time is in the OpenMP barrier routine. If only the OpenMP runtime library people implemented a better barrier routine, I would have no problems. And so I then get these messages coming down from management high up, why is the OpenMP barrier routine so poor? And that then takes a load of explanation. But that's fine.
You need an asynchronous barrier.
Yeah, exactly. And MPI has one. MPI -1 had one, because I put it in MPI -1. When we did MPI, we had this thing that we inherited from HPF, which was at the end of each meeting, a 10-minute, quarter of an hour presentation that was a humorous presentation reflecting all of the issues that had been discussed in a humorous fashion. So when we were discussing collectives in MPI 1, we came up with a non-blocking barrier for MPI -1. And of course, MPI 2 has a non-blocking barrier, and it makes great sense. It's a two-phase commit, right? I got here, I want to keep working. Has everyone else got here? Absolutely sensible. But at the time, we thought non-blocking barrier was fairly hilarious. General comparison between the two-socket type server that you've got and the Xeon Phi. So it supports two sockets, so it has coherent structure QPI in our case between the two, whereas the Phi, all of the coherence traffic is inside. So this is an SMP, right? It's not a cluster on a chip, despite what semi-accurate would tell you. He's living up to his name of being only semi-accurate. It has 4 hardware threads per core rather than 2. They're different because this is an in-order core. In the out-of-order core, the aim of hyperthreads is the observation that you have different threads are using different functional units at different times, and therefore you can interleave them smartly in the out-of-order pipe. Whereas here the idea is that you can hide latency going to L2 cache by using multiple threads. So although you've stalled up one hardware thread, another one can run. It has the wide SIMD, which gets you up to this, 2020 single precision flops or 1010. It has the high memory bandwidth, approximately 3 times the memory bandwidth. Each core has an L1D cache and an L2 cache, and there's no shared L3 cache, which there is on the other machine. Programming tools, they're the same, right? The vectors are wider, the compiler can handle that for you, but Parallel Studio, the released Parallel Studio that came out just before supercomputing supports the mic processor, the Xeon Phi processor. All of our tools are effectively the same. You can use Silk Plus if you want to. You can use threading building blocks. You can use the math kernel library. MPI runs directly to processes on the card. You can set up an MPI program where some of the processes are running on the hosts and some are on the other, and the card manages that. You can use OpenMP, including the offload technical report, which will be coming as soon as we can implement it, and CoArray Fortran and OpenCL, which we support across all of the compute things in our machine. So if you have a Gen graphics integrated on the die, OpenCL can target that. It can target the host CPUs. It can target the Phi. And then there are some more researchy type things, so like the parallel ISPC, which is a more map over style approach to writing parallelism that gives you vectorization, but is certainly research. And the offload extensions exist now, and they're not syntactically the same as anyone else's, although we believe that they're at least semantically as capable as anyone else's. We'll be moving to the OpenMP technical report versions as soon as that happens. You can compile stuff for Manycore, you can compile it for clusters, you can compile it for everything. We've had this message lots of times. MPI can run in the different places, so you can have MPI only on the Phis and treat the host as just basically not there. You can have mixed ranks MPI on the Phis and on the hosts, and then you better worry about load balancing a little bit. Or you can just use MPI on the host and use offload style to the Phi if you want to, which is more the kind of model that was being discussed in the previous presentation where CUDA was being used for the offload. And that was clearly causing some complexity in the code, whereas here you would probably do something like this one and not have to have that complexity. There's lots of stuff available. All of these things are available. So there are a couple of Intel debugger. There's TotalView. I have some affinity with TotalView since I worked on it for 10 years. Our Fortran compilers from PGI, all these different things exist and support it. My conclusions: it exists, it's real. We've delivered enough to have it intact and reach number 7. It's a coprocessor, it's not an accelerator, so just program it with open standards that everyone can agree on. And the critical point is that a bunch of the optimizations that you do to help when you port to the Phi are the same ones you need for the Xeon. And now I'll hand over to...
Okay.
Sorry, I'll hand this way.
So any questions for Jim?
Excellent.
Go on.
One slightly heretic question. You've been comparing this to an 8-core. You've been comparing this to an 8-core Intel processor. We currently have 32 cores, was X7550. How does it stack up to the processors you're currently selling now?
We've been comparing with the two-socket stuff. So we've been comparing with two-socket because that's partly because that's our standard software development vehicle for this, and partly because that seems to be the sweet spot at which most HPC people are buying machines. And so that's where we've been comparing. If you're getting twice the performance out of a 4-socket system, then you'll see half the relative performance, obviously. That's just maths.
We'll keep some time at the end to come back to more questions as well.
Okay. Thank you. So thank you for inviting me. And so in Jim's presentation, we talk about the Manycore and multi-core product from Intel, and we also talk about the programming model and the programming tools. So in the second, in this part of the presentation, we are going to address the developer issues. We are going to look at the programmability aspect of multi-core and Manycore, and we are excited here to share with you the effort that we are doing at the Developer Relations Group, try to help the developer to quickly to create a highly parallel application. And we come up with a process that leverage the similarity between Intel multi-core and Manycore, and actually taking advantage of the symmetric design of Intel development tools. So at the heart of this process or framework is a 5-step process. So what we do is that in each step, we address the very specific concerns. We take a notice that a lot of the applications are yet to be optimized, and they are actually running on serial, on scaling mode. And we actually create a process that step by step we take application to be suitable for Manycore coprocessors. So the rationale behind this is actually restore the confidence that the program has on its own code, instead of creating another API to depend on someone else who are not familiar with the problem to solve your problem. We try to restore the confidence so that you understand and you can find the way that is most comfortable for you to express the parallelism inherent in your algorithm. So the objective, as I said before, is to turn the unoptimized, the serial scalar code into highly parallel vectorized code that you can scale from multi-core into Manycore. So the first step is to find out that you are basically using the right tools. So this is one of the efforts to minimize the amount of development work that you have to be doing. And if someone else has solved the problem, you can borrow, steal, or actually buy the solution from them. It actually, we described the Intel compiler, but it doesn't have to be Intel compiler. We described the library, the optimized library, but it does not have to be MKL. So if someone else has solved the NIMPAC issue, the linear algebra issue, you might as well buy the solution from them. And it allows you to focus on the problem that you understand most and solve the problem and add the value there. So a lot of the time, especially on Intel architecture, there are so many compatibilities that bring by compiler. So some compiler are target for general object-oriented programming. Some are target for high performance. So it is very important that you select the right tools in the beginning. The second step is to actually do, before you start with any parallelization work, you want to make sure your core computational logic are optimized. You make sure that you understand the scaling potential of your application. Sometimes you take a serial problem and someone take to that and report, yes, I improved that by 5x. And another guy take over and say, oh, I improved that by 10x. So if you do a scalar optimization and understand the computational logic, you can understand is 5 enough, is 5x enough, or 10x enough, or actually 100x enough, or 1,000x enough. So if you don't do this level of optimization, you really don't know which is the answer. So at this level of optimization, you're usually concerned about, am I calculating with the right algorithm, whether the accuracy is good enough for our problem or not. So there are many ways that you can determine the accuracy. So this is if you use MKL. MKL allows you to select between high accuracy, low accuracy, and enhanced performance. So make sure you select that and you don't do additional work or redundant work that is not called for your problem. And in compiler, you can actually select a low accuracy, high accuracy, and a medium. So one important differentiation between Intel compiler and Microsoft compiler is Microsoft always set to high and the Intel set to medium. So in the medium, you are free to use any communication laws, these association laws, to optimize your mathematical expression evaluation. The second, make sure that your problems stay at the right precision, whether it's a single precision or double precision. You always try to avoid the C++ auto promotion. You always give a type. Is a floating point. I think I miss a float here. So if it's a floating point, you say that explicitly. And so when you do a transcendental function call, you also give exponent or exponent f. Exponent f is for single precision. So one of the problem people had with GCC is that actually in GCC, XPF is takes longer than EXP. So go figure that out. That's completely unexplainable. So the third is to actually understand the impact of denormal. So the denormal is a time when the floating point representation actually flows out of the normalized path. In that case, there is a different behavior. In Manycore product, it goes into a very expensive firmware solution, while in BigCore, the hardware actually solves the problem. So if you are actually have a complete control of the domain of your input, you should actually set the floating point mode fast equal 2. So which means that treat all the denormal as 0. Another way to tell the same thing is using Intel compiler and say domain exclusion equal 15 for single precision floating point. So you can actually calculate some ratios to determine how fast when you do a serial and a scalar optimization. It's basically you force everything to run in scalar mode, in serial mode, and calculate the amount of what we call a CPI. A CPI, the lower the better. If it's greater than 4, you definitely want to investigate. So after you're done with a serial and a scalar optimization, you should be able to know how much room you can scale forward. If you add a vectorization, the upper bound you can scale is 16, right? So basically, Intel offer Intel is not the Manycore product from Intel is not just a SIMD architecture. It has a SIMD component. So one of the requirement to get the performance out of the SIMD is that it likes this a structure of arrays. But if your input is an array of structures, the first of the thing is you have to do an input conversion. Okay, and the second requirement is it actually likes aligned data much better than unaligned. Unaligned access in Intel Manycore product has severely penalty than it does on Intel multi-core product. Here is a way that you can declare the static allocated memory. You just tell compiler additional alignment requirement. And here is a way to do that in static dynamic allocation, and it use so you can use a regular API, and this is part of the Unix runtime. But if you want to find a platform independent solution, you can use TBB. TBB stands for Intel Threading Building Block, and they have the same scalable aligned malloc. We'll come back to this routine later on when I talk about the case study. So another so to have a SIMD work, you have to have branchless execution. So if you branches, it will break the SIMD execution. The SIMD cannot jump into 16 different places at the same time. And that simply breaks the model. But you have enough scatter and gather, and also the masks that allows you to do conditional operations so that you can avoid jumping. Okay, in this, here is a list of the choice that you can make, but it's not just limited to this. These are a list of the ways that you can vectorize your code. And you can, and so at the bottom of the list, you have more controls. On the top of the list, you have more easy to use. So we are going. So a lot of the people are very comfortable with intrinsics. We do support that, especially in early days of compiler maturity. You do need the intrinsics to handle intrinsics yourself to get a high performance. We'll give an example on that as well. And you can actually have intrinsics wrapped in C++ class. We are going to talk about that in conjunction with the generic programming. And then, or you can use Silk Plus. Silk Plus elemental function actually allows you to describe a function that can be vectorized, so that even you call that within your SIMD loop, you will generate a vectorized code. But I'm more interested in compiler-based auto-vectorization. What this is actually you write your algorithm completely in scalar mode, and the compiler, and you specify the alignment requirement, and compiler will generate the SIMD code for you. So we'll have a detailed example on this approach. And here is a C++ array notation. That's more like writing a C++, the way you write a Fortran program, and it will vectorize that for you. Again, you still have to subject to the same requirement, like a structure of array rather than array of structure, and alignment requirement. Any questions? Okay, so I should continue. So we have additional more ratios that you can calculate. So using Intel VTune performance analyzer, you can collect a processor performance PMU events. And these PMU events will tell you if your code is execute in vector or not. And if you expect your code to be fully vectorized, then you calculate the ratio, and it's less than 8 in double precision and less than 16 in single precision, you should investigate. One way to investigate would be actually look at the assembly code. So that's vectorization is important part of the vector to get a higher performance. So this is a first step, but it's not the last step. So the second is the benefit of the vectorization is that you can make the full utilization of one core, and so. The next is an effort to have the core parallelization, or somebody would call that a task level parallelization. So basically, you want to, what you have done to one core, you make sure that every core, every thread in your system are behaving exactly the same. So so here, what you really want to do is to participate your workload as a higher level. Always try the coarse granularity first, because that actually avoids the overhead. Second, you have to create the thread creation overhead. The thread creation in Intel architecture is quite different from traditional GPU, which handles the hardware thread creation. So you really have to create once and reuse until the program exit. So try to avoid creation and then destroy and recreation again. So the second is thread synchronization actually kills the parallelism. So if you have if the number of synchronization grows linearly, the performance will drop exponentially. So and also you have to affinitize your work thread to the processor threads. So that's simply because there is a full operating system running on the Xeon 5 coprocessors. So Intel has additional tools that actually build in within it the Amdahl's law, and that can actually do some dynamic instrumentation so that it will predict if you do this, how much scale you want to look at, and how much, whether it will stay flat or scale linearly or somewhere in between. So this is the additional tool that Intel provide to help people to create a highly parallelized code. So here is the method that we provide for people to actually to add the parallelism into their problem. In the lowest, we support P threads, so that's very again, on the bottom of the scale, we have more control, a complete control about the thread creation, thread destroy, the masks, the affinity setting. On the top of that, you have more user-friendly. You deal with the problem you want to solve, and you allowed the library, the shared library or runtime, and to actually create the thread for you. So here is more like easy to use, and then there's somewhere in between. So OpenMP is the one that we are going to emphasize a lot, and we spend a lot of time optimizing OpenMP for Manycore programming. So in the end, we actually achieved the efficiency in one core, and then we replicate the same efficiency to a few cores or tens of cores. And now the second task is actually take what we replicated on tens of cores into hundreds of cores. So to do here, we have to go to extra length in reducing the memory footprint, because memory footprint, the bandwidth, is usually going to be the limit for that. In terms of flops, Manycore has many times of performance than multi-core, but in terms of bandwidth, as we showed, the number is 3x. So if you don't optimize your memory footprint, the best that you can achieve is 3x. But we have shown that if you manage the memory bandwidth, you can achieve more than 5x. So we have a lot of the floating point registers. There is a great benefit in actually compute in native mode. That take a full advantage of available registers. There are 32 of them in Manycore product. The second, we want to inline the function cores. Function core has its overhead. So if you don't so the normal traditional function core, you actually have to create a frame and push the parameter into the frame, and these are all involve memory operation. But you don't have to do that. If you use a function call from Intel compiler actually can recognize a function call and drop the sequence right into there. So they use register to pass the parameters, and they achieve higher efficiency. And the second, you have to improve the data affinity. So instead of traditional mode of allocating the memory, prepare the data before you create the threads, you pretty much have to create the threads in the outside, and for each thread, it actually prepares the data so that the data you created for execution stay close to the thread that are to be executed. Okay, and so in the end, you have to block the data and for maximum memory access efficiency. So I talked a lot of this, and I tried to make this more complicated, more architecturally interesting, but there isn't that many, and so it's all familiar to you. That's in the second part, I want to make sure that we can use this methodology to solve a real problem. So the problem that we are looking at is very traditional Black-Scholes. Basically, Black-Scholes is derivative pricing. The people involved there got a Nobel Prize, and that's actually drive the equity part of the quantitative finance. Is fundamental to a lot of the financial models. So in this particular problem, we look at 3 input streams that represent the spot price, the strike price, and the time. And then the risk-free rate and the volatility are constant, because the Black-Scholes is a constant volatility model. And in the end, you calculate a European call and a European put. So that's the mathematics there. And so you calculate this D1 and D2 first. There are some relation between these two, so that if you get D1, you don't have to do the same thing for D2, and you can get D2 from D1. And then once you have that, you call this function called CND, cumulative normal distribution function. And to calculate call, you use this formula, and you calculate put, you use another formula. So so people who are familiar with CND, you can they have inherent, there's a relationship between CND minus D2 and CND D2, and that's CND D2 is 1 minus CND minus D2. So from that mathematical, you can actually derive the put and call parity. So with put and call parity, you can actually calculate the call and expect the put intermediate subtraction or add away. So you cut the number of calculation along the way. So there's another fact that CND function is related to error function, and error function is what's provided as part of C runtime routine from Intel compiler. So, and in this workload, we are artificially to have an array of 1.2 million of these single precision input array, and we generate two array of one with core, one with put. So of 1.2 million array, and each option we artificially price that for 512 times. So for each input, we do all this valuation 512 times. So that's in essential the problem that that a lot that we received from the industry, and let's as an example, let's look at how we implement that. So before that, so here is the very simple implementation of that. So you got okay. So you got an array of floats, and you got so you do that for the data size. The data size is 1.2 million, and the repetition, as I said, is 512. And you call this Black-Scholes calculation, and Black-Scholes calculation is doing more or less the straightforward implementation. And so here is a CND function implementation, and you do that to CND within the core computational loop. So this implementation seems straightforward, but you simply don't see the performance. You actually, when you run that, compare with GCC, you get 5 million options per second, 5.3 million options per second. So I think if the internet is alive, I want to show you. So so here we can actually create on the fly. So to compile this program. So what this do is basically invoke the program, and then you compile that. So let's get this going, because it's taking a while. Okay, so it will take a while to complete. So while it's calculating that on a server back in Hillsboro, Oregon, and that's coming back to the presentation. So okay, so what's the first step? The first step, we will just replace the same compiler. So you remember the first step is leverage the optimizer tools and the library. So you replace the compiler with ICC, and you basically pass the same level of optimization switch. Because that Intel C runtime offer error function, you take advantage of that. Instead of rewriting a hunk of code, you actually replace the CND with error function. And this error function requires you to scale your input. And when you get the output, you scale the output. You do a simple transcale. And the performance you get is amazing. That's simply because, as I said, a lot of transcendental function calls on GCC, actually floating point takes longer than double precision, for no reason. So that's from the different expectation. And for Intel, the default for accuracy is set to fast rather than safe. Okay. So let's come back. So it hasn't. So I haven't got my prompt back yet. So so the performance is astounding. It's 4.25. I got a question.
Do both compilers inline automatically?
I don't think GCC will inline automatically, but
It depends on the source and exactly what your question is. One thing GCC doesn't do in O2 is loop unrolling, and it doesn't default to fast math, which is your massive medium thing.
okay.
And the speed of the exponent routine is actually measuring the performance of the library, not the compiler.
Oh, okay. Yes, so that's the difference between open source implementation of the library and.
GCC will inline static functions automatically,
Okay.
even if they're not declared inline at O2.
Yeah. Yeah, so one of the two aspects that set Intel compiler apart, one is the inline. Intel does inline aggressively. And even if you don't ask, it will inline. So,
So we've only got 5 minutes, Shuo, so you need to...
oh, we have only 5 minutes. Okay. So maybe let's keep on running the... yeah, it hasn't come back yet. So it's a mistake to run that on scale mode. So, okay. So the next is to do a scalar and a serial optimization. So to do a scalar and serial optimization, you just optimize without using additional hardware resources. So you can't expect a big improvement, but you can optimize your calculation. One of the optimization I've done here is put in core parity, which comes really from mathematics. So once you get a core, you do a subtract and add away from doing a put, and that actually gives you some improvement. So you basically, in this level of scalar and serial optimization, make sure everything stays in float. So whenever you do a constant and a function call, make sure you give an explicit type. Vectorization. So vectorization, as I said, is to fill all the SIMD names. So the one that that I used in this particular problem is called a compiler-based auto-vectorization. So so compiler, you allowed the compiler to vectorize your serial code. You give the serial code, but in addition, you give a little bit hints as to whether it's aligned or not, and whether it can be a pragma or not. Pragma SIMD forces the compiler always to vectorize. Even sometimes the compiler determines it's unprofitable to vectorize because vectorization, you really need performance. Vectorization is simply the means. With a lot of the instruction improvement, you can actually scatter and gather yourself into a vectorized code, but that vectorized code will not give you a higher performance. So if you add the pragma, then you do this aligned malloc. That's all it requires, okay? And add the pragma SIMD to the core computational loop. This loop will be vectorized, and you will achieve 5.6x performance improvement because vectorization does have its cost. Sometimes the you're setting the mask. So 8x is a goal, but it's not always. So there's also a parallelization aspect from Intel Manycore. So in parallelization, it's very simple. You just use OpenMP runtime, and then you have to have a strategy as to where you apply the parallel. As I said, the parallelization should be applied on the outside. Always achieve the coarser granularity first. And you use your vectorization in your inner loop. If you have a two loop, then the task is easy. You vectorize your inner loop, you parallelize your outer loop. And so adding OpenMP to compile, and then you can achieve 17x improvement. So that's the step 4 for parallelization. Basically, you fill all the lane, and then the next step would be to scale from tens of cores into hundreds of cores. So again, we talk about the NUMA friendliness because you are creating 240 threads. If you create all the memory within the manager thread, there's so much scalability. The remote memory and the closed memory is going to average. You cannot scale that too far. And so you have to create a thread and then allocate the memory. And then you do this affinity, so make sure the work thread are mapped and run before it closes, before it ends. And then data blocking, simply add another block to the data so that you can actually achieve your memory access efficiency. And then Intel Manycore product support streaming write. So the streaming write is a write operation, or is called a streaming store. It's a memory operation that is optimized in the sense that it will not cause a prefetch from the memory to the CPU, because you write once and move quickly to the next element, and you don't want to prefetch the next element, first read it before you write. So this actually save you a request for ownership and also a memory. So what you have to do is you tell that I'm going to write two arrays, two floats, core result and put result, and those are non-temporal. So don't prefetch that to the memory to be read before I write, because I want to write unconditionally. And another thing is about this many integrated core, we create a hardware transcendental function, exponent and log. So a lot of scientific computing using the natural-based log, and say that if you calculate the log of arbitrary base, like 60, so how are you going to do that? So the professor will tell you, oh, why don't you convert that into a natural base, and then we calculate from there. But if you talk to architect, the architect actually can implement the log 2 base or exponent 2 base much faster. So it costs only one instruction. So instead of you convert your log into the natural log and have Intel compiler convert into the exponent, you actually can directly go from your base into base 2 and achieve the performance gain. And that's the area where it gives Manycore on a lot of the financial kernels higher than 5x performance improvement, because all these the natural-based exponent and the log are used a lot in financial calculations. So if you do that, we can actually improve that from 5 million options per second into 20,000 million options per second. So that's the level of performance we talk about. So here, to run the same Black-Scholes natively, what you can do is, so you compile that in step 4. After step 4, you get a parallelized and vectorized solution. And then in Manycore, once you addressed all the issues, the affinity issues, the log exponent issues, you prepare something that you can run many integrated core. And then the next step is that you actually use the SCP to copy your program into your card. So this is doing, so you make the card, you address the card the same as if it's another IP node. And then after that, you try to obtain a login. So you do this sudo SSH from your host into your Xeon file coprocessor, and then you go to there, set the environment variable, because we do use the TBB for memory allocation, and then off you go. So on the Xeon processor, you can comfortably reach 3.8 billion options per second. But in the Xeon Phi, you can further reach 20 billion options per second. So that's how to run the Xeon Phi native application. So so I have another example, and then maybe 5 more minutes.
We're kind of over time now. So
Okay.
is there any way you can sort of
Sure.
to wrap?
Yeah. So we talk about the native to run the native application. So I'm going to wrap up and give you a quick tour of running on offload application. So it is also possible to use Intel Xeon Phi as a offload application. So I'm showing you an example that I created for SC10. So it has 2 scenarios. You run unoptimized code, scalar and serial on Intel Xeon, and you get one set of the performance. The second, you optimize using the structured Stepwise framework. You create the parallel code you can run on multi-core product. In scenario 3, you run a portion of your problem on multi-core and run another portion on Manycore. So you build all this on the C vector class, which is very valuable before you get a compiler to do any vectorization and creating a SIMD code. So that's all you need to actually wrap the intrinsics with C++ class. And then you generate this type-independent or SIMD-independent implementation of your algorithm. This is Monte Carlo, this is binomial, and it takes advantage of the class that I just described earlier. And then on top of that, you use the generic programming, which is invented for C++, to manage the complexity. So you create 2 OpenMP sections. In the second section, you say, if I was asked to use the Xeon Phi coprocessor, I will offload this as an input and receive this as output. When you implement this Monte Carlo, you say, if I was asked to offload, I instantiate one set of a template with my predefined class. And if I was asked not to offload, we create another set of template. So in the end, the performance would be, so if you run that unparallelized, you takes a long time. It's probably 800 seconds to 1,000 seconds to complete. But if you run that, if you parallelize your code, if you run that, you shaved 90% of the code. If you run that, part of the problem on Xeon Phi coprocessor, you achieved another 3x performance improvement. So that's how my tutorial. The first of things, so we talk about the product announcement. So more importantly is we talk about the similarity from the programmer point of view, the similarity between Intel multi-core and the Manycore product from Intel, and also the symmetrical design of the Intel tools. So what it allows you to do is to forward scale your application using Intel tools and this methodology, and turn your multi-core program and scale them into forward scale them into Manycore. Sorry.
Great. Thank you very much, Shuo and Jim. Thank you. So I know we're a few minutes behind, but I imagine this is going to be quite an interesting subject for people. So rather than rush on with no questions, we'll take a couple of minutes for questions. So who would like to go? And do we have the other mic? The other mic's up at the back. So who's going to be? I'll run along this way past the mic.
Okay, so first a quick question as to whether you'll make the demo code available on a website somewhere so people can take time to actually go through the code and look at all the changes you've made.
Yes, I will.
Okay.
That's not a problem.
And so somehow we'll get that information back to Simon.
Yeah.
Great.
Okay, well, if you let me know where it is, I can put it on the website to go with this.
Okay.
Because all of these slides and the recordings should go on the website hopefully by the end of next week. So we'll
didn't mention, one thing we should mention is that there's a site that's just gone live today, which is software.intel.com/mic-developer. If that's a primary place to go and see all of this kind of information and tutorials and all of those kinds of things should be there.
There's one over here.
This could be the dullest question of the day. When you've done all this parallelization and optimization, did it produce the same results as a serial code?
Yes, to a certain extent. So we use the same. Validation. When we do our optimization, we have a validation routine that calculates everything in serial, and we make sure that those are close enough, which means that if you use single precision, your relative error should be less than 1e minus 7.
Okay.
Anyone else? There's another one down on your side.
Just be there. Excuse me.
Tobias Pranik from Cambridge. I was wondering about these large vector types. One of the problems with using it in practical applications is actually getting the data into the registers and then getting the data out of the registers when you've done your computation, especially if you need to gather data from multiple memory locations and then scatter afterwards. I was wondering if there's any facility for that in Intel Phi.
Yeah, the Phi has some instructions for gather step and scatter step instructions that are intended to help with that. But of course, if you're but they still work best if you've already got the data in L2 and if you're using everything, all of the data that you move. I mean, if what you're doing is moving a whole cache line in, 64 bytes cache line in, and then operating on 4 bytes of it, you're going to blow your memory bandwidth no matter what you do. No matter how you express that with instructions, isn't going to overcome that fundamental limit. So you still ideally want to have your stuff nicely contiguous in a structure of arrays format rather than array of structures. We don't have any magic.
Probably time for just one more.
Come back up here.
Jonathan Hogg, STFC. So you've given lots of examples in C. Can you do the same sort of things in Fortran with the memory alignment and things to achieve the vectorization, which is obviously C has a lot of keyword support for attributes and things, but Fortran doesn't really have a portable standard. Is it possible to do that in a portable way?
It's possible to do it. As to the portability, I'm not entirely... It's certainly possible to do it in Fortran, and as to the portability, I'm not entirely sure. But you can certainly request that things be aligned, and for allocatable objects, you can request that they're allocated aligned.
Good question. So we'll have to leave it there because we're running a little bit behind, but let's thank the speakers again. Thank you, guys.